Yes, so we are live. All right,
Cool.
so welcome to talk on the Shannon channel. So today I'm very happy to have Ilan Shomorony with us. He's a postdoc at UC Berkeley, and he's going to talk about designing algorithms based on information limits. So this is a live talk. If you're interested in joining these, you can go to the webpage. Okay, and then if you also you can also watch this talk on YouTube. So if you're watching it on YouTube, so you can also watch it live and ask the speaker questions. So again, so Ilan, I'm happy that you are giving the talk, and then I'll give you the
All right. Thank you very much. Thank you all for being here, I guess. And yeah, thank you, Salim, for inviting me. It's my pleasure to be part of season 1 of the Shannon channel. Can you guys hear me? Can everyone hear me? Cool. So yeah, I'm excited to be telling you about some of my recent work on DNA assembly. Let me try sharing my screen here to see if you guys can see my slides. Can you guys see it? Can anyone say
Yes.
something? Oh, okay, cool. All right. So yeah, so this is some recent work that I've been doing on the DNA assembly problem, and I've been fortunate to be working with like a lot of great people: Tom Curtay, David Shea, Sam Kim, Govinda Kamath, and Fei Xia. I have to say that because some of them may be hearing this, and so I'll be talking about this idea of designing algorithms based on information limits. And what I hope to convey to you is that sometimes by looking at a problem and focusing on the information limits rather than the sort of like more traditional approach, which is to focus on the computational aspects of the problem, may reveal some new insights to the problem and may lead to the design of new kinds of algorithms. Okay, in this particular case, to apply to the DNA assembly problem. So since I assume this is a diverse audience, let me start by telling you what the DNA assembly problem is. Okay, and feel free to interrupt me at any time. Okay, so I hope everyone can follow this. So the DNA assembly problem is a problem where we're trying to figure out the DNA sequence of a given organism. So the DNA sequence is we will refer to it as the sequence S, and it's a sequence of length G, and G stands for the genome. Okay, so in general, this is a very long sequence. Okay, so for bacteria, it can be like in the order of 1 million bases, and for humans, it can be in the order of 1 billion bases. And so the issue is that we don't have a technology that simply takes these DNA molecules and reads it from beginning to end. So instead, how do we figure out these sequences? Okay, so we do something that is called is there any question or? Okay. So we do something called shotgun sequencing. Okay, so shotgun sequencing is the idea that instead of trying to read the whole sequence end to end, we take a bunch of short reads from some unknown locations of the sequence. Okay, so basically we run the sequence this DNA molecule through something called a shotgun sequencer, and what this thing gives us is a bunch of little substrings of this long sequence. Okay, and our goal in the assembly problem is to take all these substrings and design an assembly algorithm which takes all these little sequences and assembles them in a coherent manner. Okay, so our goal is to reconstruct this to estimate the original sequence S, right? So we'll come up with some sequence S hat, which is our estimate. And of course, our goal is to achieve what we call perfect assembly, which is to reconstruct the original sequence correctly. Okay, so that's what we mean by perfect assembly here. So now, in this talk, I want to focus on sort of like a formal, like a formulation, a mathematical formulation of this assembly problem, and I want to contrast two distinct points of view for this problem. Okay, and I want to use this figure here. Some of you may remember this from ITA a couple of years ago. Okay, so I have Claude Shannon on one side and Alan Turing on the other side to represent these two views. Okay, so maybe Alan Turing would approach this problem from a computational complexity point of view, while Claude Shannon would approach this problem from more of an information limits point of view. Okay, so what exactly do I mean by that? Okay, so Alan Turing would maybe look at this DNA assembly problem, and first he would try to come up with some mathematical formulation of it, which is usually in the form of some sort of combinatorial optimization problem. Okay, so for instance, one classical formulation for the assembly problem is the shortest common superstring problem. Okay, so what does that mean? It means that if I bring back that picture from the previous slide, where you start with your sequence, right? It goes through a shotgun sequencer that gives me a bunch of little strings, and my goal is to design an assembler. Maybe the approach here would be to say, well, maybe the assembler should be looking for the shortest common superstring, right? So the shortest string that contains all these little guys here as substrings. Okay, so now usually what happens is when you formulate the problem, okay, so here let's say if you formulate the problem as the assembly problem as the shortest common superstring problem, what happens is you end up hitting an NP-hard formulation. Okay, there are more than one formulation, and they all end up being NP-hard. Okay, and what do people do when they find an NP-hard problem? Well, they say, well, we're hopeless here, and instead, let's try coming up with some sort of approximation algorithm or just some heuristics, because there's no hope of really solving this problem in practice. Okay, so just for instance, some people have tried following that path, and a lot of people have tried to find approximation algorithms for the shortest common superstring. Okay, so for instance, people have been proving that a greedy algorithm actually approximates this shortest common superstring to, so currently the best known factor is 2.47. And there's a conjecture that says that it actually approximates to within a factor of 2.
So what would be the greedy algorithm?
So the greedy algorithm essentially takes these substrings here, and it finds the two substrings with the largest overlap and merges them. And then now you have a new set of strings, and then you keep repeating that.
And what if there is no overlap?
Then you just view it as an overlap of 0. And then you basically glue two things together with no overlap.
Oh, okay.
Right? I mean, okay. So that's a view, and it's sort of a pessimistic view in a way, right? Because you say, well, it's NP-hard, so let's just try to find some approximation algorithm, and it's not very clear whether this is the right way to look at this problem, and because it's not very clear whether we're really solving the assembly problem anymore. Right? It's not very clear whether, even if we could solve the shortest common superstring problem exactly, it's not very clear that this S hat here actually equals the true sequence. Okay, so it's not very clear that the shortest common superstring is the right problem to be trying to solve here. Okay, so now the alternative approach that I want to tell you about is by first focusing on information limits instead. Okay, so this approach would start with a different question. Okay, it would start by looking at this data here, the data that you get, which is the set of reads, and asking how much data do I need to even be able to achieve perfect reconstruction. Right? So because you can easily imagine situations where you only have very few reads, or the reads are too short, and it's not enough for me to, there's not enough information for me to reconstruct my true sequence S. Okay, so then once you understand this, when there is enough information, then you can try designing algorithms which are sort of like guided by these information feasible instances, right? Algorithms that work when it's possible for them to work. Okay, so now in this talk, I'll be mainly focusing on two questions which come from this approach. Okay, so the first one is, so let's suppose we do that, right? We try to design an algorithm that focus on these information feasible instances. Okay, so can this avoid this apparent NP-hardness of the assembly problem? Okay, because you can say that, let's say, find an analogy in information theory. This is what happens in the channel coding problem, right? Because the decoding of an arbitrary code is in general NP-hard, but once you focus on well-designed codes that whose rate is below the capacity, we know that we can find efficient algorithms to do that. So maybe the same thing happens here, and we can actually sort of like dodge this NP-hardness. Okay, that's the first question. And the second question is, well, this is just half of the picture, right? I mean, I cannot just focus on the information feasible instances, because what happens in the information infeasible instances, right? In the information limited instances. Okay, so I usually don't like outline slides. I think they're kind of boring, so I'm just gonna show you here very quickly what the outline of the talk will be. And basically, I'll be focusing on these two questions. Okay, so first, regarding the first question of this NP-hardness issue, I'll present an algorithm, an efficient algorithm, which can solve the assembly problem only in the information feasible instances. Okay, so in fact, by focusing on information feasible instances, we actually avoid this NP-hardness. And then, time permitting, I'll talk a little bit about what happens in the other instances, and I'll take sort of like a classical information theory approach to that and say, well, if I can't reconstruct, maybe I can reconstruct things to within some distortion, right? And then I'll try to motivate a rate distortion perspective to the problem of partial assembly. All right. Okay. So first, I want to talk about this this algorithm for doing assembly in the information feasible instances. And of course, first we need to ask, what are the information feasible instances, right? When is perfect assembly possible? Okay, and we were not the first people to ask that question. Okay, in fact, a couple of years ago, this guy here, Eugene Myers, who is a pretty famous bioinformatician. You can tell that he's famous because his Twitter profile name is the Gene Myers. That means the guy is famous. And he tweeted about 2 years ago. He tweeted a theorem trying to answer this question. Okay, so he says that perfect assembly is possible if and only if three conditions are satisfied. So the first one is that errors should be random, the sampling should be Poisson, and the reads should be long enough to solve repeats. Okay, so as you know, a tweet is only 140 characters long. So he ran out of space, so he couldn't prove this theorem, right? But the main reason why he stated this theorem in the first place is this this third condition here. That's what I want you guys to focus on. So he says that the reads should be long enough to solve repeats. Okay, so why did he say that? The reason is because Gene Myers realized that the sequencing technologies, the long-read sequencing technologies, have been developing very fast recently. Okay, so for instance, there's this company, this sequencing company called PacBio, and they build sequencing machines, right? And they are generating reads that are longer than 10,000 base pairs long. So these are very long reads. Okay. Moreover, they claim that their sampling, the sampling of these little reads, is essentially uniform. Is essentially these are coming uniformly at random from the sequence. So which is essentially what Gene Myers is referring to as this Poisson sampling. Okay, so it seems that the technology is going in the direction proposed by Gene Myers in his theorem. But of course, this is not a very concrete theorem, right? He doesn't say what it means for a read to be long enough. And he says that the sampling should be Poisson, but he doesn't really say like how many samples you need. Okay, so a more formal treatment of this question should be really concerned with these questions, which is what read length is actually long enough, and what coverage depth, and by coverage depth here I mean the number of reads that cover any given position in the genome. So essentially, coverage depth is, you can think of it as the number of reads. Right? So essentially, what read length and number of reads are actually required. Okay, so he just said, oh, it should be Poisson and it should be long enough, but he didn't say exactly how long, how many samples or how long they have to be. Okay, so then to ask this question a little formally, right? We can consider this idealized setup where we have a sequence S, okay, going through this well, let's imagine an ideal sequencer that does uniform sampling. Okay, so it generates, let's say, n reads, and each read has length L. So now we have these two parameters, n and L. And our goal, and let's assume that in this idealized setup, the reads are error-free, right? So they're exact substrings from the sequence S. Okay, and our goal here is to design an assembler, right, or an assembly algorithm, which takes these reads and tries to reconstruct the original sequence S, right? This similar setup that I showed you before. Okay, so now we have these two parameters, n and L, and the approach that was proposed a few years back by Bresler, and Shea is that, well, maybe we should try to characterize the n, L feasibility region for this problem. Okay, so what does that mean? It means, well, I plot n versus L, and my goal is to figure out the set of points where it is possible for me to reconstruct the original sequence S. Okay, so now such a region should be sequence specific, meaning different genomes. For example, maybe I want to characterize the region for E. coli or some other organism. And the reason is because some genomes are harder to assemble than others, right? And the genomes that are harder to assemble should have smaller feasibility regions. So this region should capture the difficulty of assembling a given genome. And what they did in their paper was they tried to come up with some information-theoretic bounds for this region. Okay, so just to give you some ideas, one such information-theoretic lower bound is this critical read length, which was previously known in the literature in papers by Yukonen and Pevsner. And basically, this is a number, right, a critical read length, which is a function of the sequence. And below this read length, it is impossible to achieve this goal of perfect assembly. Okay, so that's one first lower bound. They also have a lower bound on the number of reads. Okay, so this lower bound is what's called and it was also known previously, is the Lander-Waterman coverage. So the Lander-Waterman coverage here is just the number of reads that one needs to take from a sequence to make sure that every base in the sequence is covered, is seen at least once with high probability. So it's kind of like a coupon collector type of phenomenon. Okay, so
I have a question.
Yeah.
Is there an intuition behind why is there a lower bound on L?
Yes. So the reason is because real genomes. Thank you for the question. Actually, I should have mentioned that. So the reason real genomes have very long repeats. Okay, so they look nothing like IID sequences, or so they have these very long repeats.
I see.
And the problem is, once you read, it really depends on the specifics of the repeat structures. But if your read is too short, then it is impossible to figure out how these repeats connect to each other, and you know how they are organized in the genome. You get confused.
Okay.
Does that make sense?
Yeah.
Cool. Okay, so now the lower bound on n is this Lander-Waterman coverage here. So what they did was they normalized this y-axis by this number, and then now the lower bound now is just 1, right? So below 1 here it's again impossible. So what they did in the paper was they generalized these two lower bounds, and they actually got a nice curve like this, and they showed that below, to the left and below this curve, it is impossible to assemble. Okay, so that's the negative part of their result, but they also had a positive part of the result. So in fact, they proposed an optimal assembler, okay, which essentially achieves all the points outside of this impossibility region. Okay, so there's actually a little gap between these two regions, but for practical purposes, we can think of them as basically matching. So essentially, they propose this assembler, which reconstructs the correct sequence whenever it is possible to reconstruct the correct sequence. Right? So this, in a way, characterizes the information limits for perfect assembly, and it should be the end of the story, right? So what am I going to talk about here? Is the problem completely solved?
I have a question, Ilan.
Yeah.
So what do you mean by impossibility?
Yeah, that's a good question. So I mean, you should think of it as impossible, meaning no algorithm can really be able to tell. So usually what happens is, for example, if the number of reads is below Landry-Waterman coverage, right, then with a certain probability, you will have certain positions, certain characters in the sequence that are never seen.
Okay.
So then there's no hope of really reconstructing the true sequence in that situation, right? So that's one situation. Another situation is that when the read length is below this L critical, then what happens is it's impossible because there are different sequences that have the same likelihood, but you just can't tell them apart.
Okay.
All right. Okay. So then they basically characterize these limits, right? And what's left to do here? Okay, so the issue is that they use this optimal assembler here, and the question is this optimal assembler a practical assembler? In particular, in this new trend of long read sequencing technologies, the question is, does this optimal assembler they came up with can it be used for long reads? And unfortunately, or fortunately for me, it cannot. Okay, so this optimal assembler is not suited for long read technologies. Okay, I'm not going to go into much detail on why it cannot, but I'm just going to tell you that it is based on something called De Bruijn graphs. Okay, which is a framework for designing algorithms, assembly algorithms, that was very successful in the last decade, but it was very successful for short reads with low error rates. But for long read technologies, De Bruijn graph approaches are not very good.
By long read, do you mean L is large?
Yes, exactly.
Okay.
Yeah, so just to give you an idea, so yeah, so as I mentioned before, PacBio is generating reads now that are on the order of 10K, right? And the previous second generation of so this is what we call now third generation of sequencers, and the previous generation, the second generation, was actually generating reads of length 100 to 200. Okay, so now the reason why this De Bruijn graph approaches are not very good for long read technologies is because in De Bruijn graphs, the first thing you do is you take the long reads and you shred them. You extract all the k-mers. So k-mers are length k substrings. So you extract all the length k substrings of all the reads, and you build a graph to try to assemble. Okay, so this goes against the idea of trying to take advantage of the long reads, right? Because the first thing you do is you shred the reads down to very little k-mers. And the other issue, which is perhaps the more important issue, is the fact that all long read technologies have high error rates.
What is the k-mer again?
So a k-mer is a length k substring of a read.
Oh, so you have to extract all these?
Exactly. Yes. So the way you build a De Bruijn graph is you fix some parameter k, and then you look at all the reads, and for each from each read you extract all the length k substrings, and you create a node in the graph for each of these length k substrings.
And these substrings have to be contiguous, or
Sorry, I couldn't hear you.
The substring, what is the substring? Does it have to be, the letters have to be?
Does it have to be letters?
I mean, the substring, does it have to be contiguous next to each other in the superstring, or it can be any substring?
So you extract all of them. So all the, so you take you take the first one, you take each read, and you take the first length k substrings. Then you shift one position to the right, and you get the second. And for each one, you create a node. So basically, you get essentially n times l or n times l minus k nodes in your graph.
Okay, thanks.
So are you just reformulating the problem with L equal to K and larger N?
So
by shredding it into
yes, in some sense, yes. I mean, it is. You shouldn't think of this as reformulating the problem. This is an algorithmic approach to assembling things, right? Yeah. I mean, I don't want to spend too much time on this the Bruin graph stuff because this is not what I'll be talking about. But yeah, I can give you more details later.
Okay.
But because the point is that for long read sequencing technologies, people don't use them anymore because they don't work, right? Because they're very sensitive to read errors. And essentially this graph, because the high error rates of long read sequencing technologies, these graphs don't really, they lose their structure. The structure gets ruined by these error rates. Okay, so what people do in practice with long reads is they use something that is called, it's perhaps the most natural approach to assembly, which is overlap-based algorithms. Okay, so what's an overlap-based algorithm? Well, you simply take read, and a read here is very long, so you should think this is a very long sequence, and then you identify another read that has a long overlap with it, and you merge the two, right? So that's kind of like similar to that greedy algorithm that I mentioned at the beginning, right? So you just identify reads that have long overlaps, and you just merge them, right? So why is that good? This is good because this is robust to errors, right? So if there are, let's say, some insertions, some deletions, some substitutions here, since the reads are very long and the overlaps are very long, you should still, at least in principle, be able to identify these overlaps. I mean, how to do it is a different story, but in principle, you should be able to do it. Okay, so that's what people want to do in practice. They want to do overlap-based approaches. Okay, so let me elaborate on this a little bit more. So in practice, what people do when they want to assemble with an overlap-based assembler, they create something that is called a read overlap graph. Okay, so the read overlap graph is you start with all your reads, your full reads. You don't shred anything down. These are your full reads. I mean, they look short here, but you should think of these guys as very long. Okay, and what you do is you identify overlaps between them, and you place edges between these guys, and with weights that correspond to the length of the overlap. Okay, so for instance, here, this read here has an overlap of 4 characters with this read. Okay, so I place an edge like this with weight 4. Okay, so I create my graph like this, and then once I construct the graph, right, I want to identify my true sequence on this graph. So I'm looking for a path that visits every node on this graph. Right, that's my goal here. And so if you recall, a path that visits every node on a graph is called a Hamiltonian path. Right, so my goal here is to find a Hamiltonian path on this graph. Okay, so the issue is identifying a Hamiltonian path on a general graph is in general NP-hard. Okay, and that's actually why this the Bruin graph business that I mentioned to you before was very successful, because what they showed is that on a De Bruin graph, and again, I don't want to talk about this too much, but on a De Bruin graph, the true sequence actually corresponds to not a Hamiltonian path, but an Eulerian path. So an Eulerian path is a path that traverses every edge on the graph. I mean, also every node, but it traverses every edge. And it turns out that finding an Eulerian path is much easier. I mean, it can be done in linear time, while finding a Hamiltonian path is NP-hard. Okay, so the problem is, as I mentioned to you before, the Bruin graphs are not good for, they were good for short reads with low error rates, but when we're talking about long reads with higher error rates, they are out of the game. Okay, so we can't do that. So instead, we're stuck with this read overlap graph and trying to find a Hamiltonian path. And that's kind of like the problem that I want to tell you about today. Okay, so our main contribution is a way to try to attack this problem. Okay, so our main result is an algorithm that can still, even though this problem is seemingly hard because it's a Hamiltonian path problem, I'll tell you about an efficient algorithm, okay, which constructs a sparse version of this read overlap graph. Okay, so meaning I'm gonna delete some edges of this graph, okay, making the graph a little sparser. But as it turns out, in this sparse read overlap graph that we create, the true sequence will correspond to an Eulerian path also. Okay, and that can be found efficiently.
Just to confirm, you're still dealing with error-free reads, right?
Yeah. So for the formulation and the theorems, we're going to be assuming this idealized model where you have error-free reads. But the point is that now we're using a framework, which is read overlap graphs, which is robust to errors. So the hope here is that by coming up with algorithms for this framework, for the read overlap graph framework, they will translate better to the situation with errors. And at the end, I'll show you some recent results where we try to do that, where we try to take the ideas designed here and apply them to the setting with errors.
But what makes you think the overlap graph is more robust to errors? What is the intuition?
So the intuition is the fact that identifying overlaps can be done in a robust manner, right? So it's like this little picture that I had here on the bottom, right? So identifying overlaps is in general something that can be done in a robust manner because you're talking about very long reads, okay? And so the overlaps between them are also, I mean, intuitively long. So even with higher rates like 15%, there is enough conserved parts in the overlap that you should, in principle, be able to identify them.
For example, so each of these things will appear in many reads, so you can do like decoding or something like this.
So that's a sort of a separate issue, which is at the end, you will use this redundancy that you get from the fact that this appears in many reads to actually decode, to actually, to correct the errors.
Oh, but here when you're doing the graph.
For the graph construction, you can actually do this in a pairwise manner. You can actually identify pairs because under the assumption that the overlaps are long. Right, so you're talking about reads of length like 10,000, right? So the overlaps between them are of the order of a few thousands, right? So even if you have a rate of 15%, you should still be able to tell that. I mean, I'm being vague here because I don't want to get into the details of how to do that. Okay. There are techniques to do that, and I can tell you more about it. But I kind of just want to see it as a black box.
Okay, so just to understand now, the graph is these deletion colors that you have in this slide, right?
So the graph you build by so here you have your reads, and these reads may have deletions, insertions, and so on. But then you have a way of checking for each pair of reads the size of the overlap.
Oh, so you will weight the edges in a different way. There is a way to do it.
But the weight of the edges corresponds to the size of the overlap, which, yeah, it changes a little bit because of insertions and deletions, but it's not really affected that much. But the difficulty is in identifying the overlap, because things don't match perfectly. But
Okay.
but you can imagine, right? If I give you two reads, right, and you can kind of like imagine sliding them on each other and computing sort of like likelihoods and stuff
Sure.
to test what's the right overlap between the two. But yeah, there are ways to do that efficiently also.
Okay.
Okay, so basically we have this graph, right? And our goal is to, even if I was given the graph, so as you can see, even constructing this graph is hard. But the problem I'm going to be telling you about here is more about the second part. Once the graph is constructed, what do you do? Because even then the problem is hard, because you have to find a Hamiltonian path, right? And the technique that we'll present to you is a way to sparsify this graph, so that at the end of the day, the true sequence actually corresponds to an Eulerian path on the graph, which can be found efficiently. Okay, now the little caveat, and this is what ties with the title of the talk, is that in general, if you recall this, we have this feasibility region, right? This N versus L feasibility region, and we will only be able to do this reduction here for points that lie inside this feasibility region. In other words, if it is possible to do assembly, then we can actually sparsify this read overlap graph and get a new graph where the true sequence corresponds to an Eulerian path. Okay, so now I want to talk about sparsifying a graph. Okay, and let me first quickly mention a tool that a technique that is used in some real assemblers to sparsify a graph, and it's a very simple idea. It's the idea of simply using a minimum overlap threshold. Okay, so I have my read overlap graph here, and I'm simply going to set some threshold theta and delete all the edges below this theta, right? So for example, if I set my theta to 1, I delete a bunch of these edges. If I set it to 2, I delete some other edges, right? And the hope is that by deleting some edges, right, I'll make it easier to identify the true Hamiltonian path on this graph. The problem is that I don't know where to stop, right? If I increase theta too much, I may end up start deleting some of the true edges of this path, right? And in general, I don't have a genie to tell me what's the right theta. Okay, so to emphasize this point, we did a little experiment here where we took the genome of E. coli and we generated 10,000 reads of length 3,000, and then we constructed this graph and considered varying this theta. Okay, so notice that since we know the ground truth here, we know the E. coli, we know the true sequence on this graph, so we can see like what are the missing edges and what are the spurious edges. Okay, so we plotted this for the case of E. coli. Okay, so here what you can see is I'm varying this minimum overlap theta, and we see a trade-off here, right? So if I make theta too large, I kill my unnecessary edges, my spurious edges, but at some point I start also killing a lot of the true edges and having a lot of missing edges. So there's a tension between these two things, right? And there isn't a good theta that kills everything, that kills all the missing edges and all the spurious edges, right? So that's why this approach is in general not good, right? This approach of just using a global theta to sparsify the graph. Okay, so that's one very simple idea of to sparsify the graph. Another approach is related to that greedy algorithm that we mentioned in the beginning. Okay, so what would be a greedy way to sparsify the graph? Well, it would be to simply take each node on this graph and pick the best, let's say, outgoing edge on that node. Okay, so this will give me some sparsified graph like this. And hopefully, maybe we can hope that by doing this sparsification, you're left with a graph that is the true sequence, right? It would be very lucky to if that happened, but maybe this happens, right? And you can ask when this happens. When does this happen? When does this greedy approach generate a graph that contains the true sequence?
So how is this different than the greedy approach you mentioned in the first slide?
It's exactly the same. This is the greedy approach seen from the perspective of the read overlap graph.
Oh, okay.
So that's what it corresponds to when you're looking at the read overlap graph. You can sort of like see it as also a sparsification technique.
Okay.
Right. So now the question here is, when does the greedy approach work, or rather, when does it fail? Okay, so it fails if the sequence has long repeats. Okay, and in general, real genomes have long repeats. And let me show you why this fails. Okay, suppose here this is my genome here. Okay, and it has two repeats. These yellow segments are repeats. Okay, so what happens is I may end up getting a read. This green segment here, let's say this is a read. It's a read that falls inside this repeat. Okay, so now I cannot tell whether this guy came from here or from there. So really, the true path on this graph that corresponds to my sequence should visit this read actually twice. Okay, so we should have a path that visits that same read twice. That's the natural thing to do, right? Because in general, I don't know where this read came from, so the path should visit it twice. Right? It might as well have come from both places. Right? The problem is, this is what's called in the literature a generalized Hamiltonian path. Right? It's a path that visits every node on the graph at least once. So it's allowed to visit some nodes multiple times. And the problem is that the greedy algorithm fails here because it doesn't allow this to happen, right? It doesn't allow this node here to have two outgoing edges. Right? So in general, the reason why the greedy approach is not good is because of this. Because if my reads are shorter than some of the repeats in the sequence, this may happen. Okay, so this can also be understood from the perspective of that feasibility region that I mentioned before. Okay, so you can ask, in what points here does the greedy algorithm succeed? And you can compute this, and it looks like something like this. Okay, so it basically succeeds when the read length is longer than not L critical, but L repeat. So L repeat is essentially the length of the longest repeat in the sequence S. Okay, so for the greedy algorithm to succeed, you need the read length to be longer than every repeat in the sequence. Okay, but this is in general like very far from the true feasibility region here, the blue curve. Okay, so this vertical asymptote shifts to the right by a lot in general. Okay, so now our algorithm, the algorithm that we propose, is inspired by the greedy algorithm, but we try to essentially get all the points in the feasibility region as well. Okay, so the point is that we don't want to be too greedy, right? So because of that, we call our algorithm the not so greedy algorithm. Okay, because it's basically inspired by greedy ideas, but we're not too greedy. We allow some of these things to occur.
Typically, what's the value of L repeat, say in the E. coli example?
Ah, good question. So I think it's in the order of like 10K.
But 10K was the L.
Yes, that's right. So in the case of E. coli, we're getting into the regime where the greedy algorithm by itself would work. So I mean, so in practice, of course, the reads are not exactly 10K. They have variable length and all that. So yes, so it's true that for E. coli, the greedy algorithm, depending on the specific data set that you have, the greedy algorithm may work. But in general, right, when you're sequencing some new organism, you don't know the length of the longest repeat.
Right.
And E. coli is a relatively simple genome, right, and very small. So when you start sequencing more complex organisms, you expect that even the long read sequencing technologies are not going to be provide long enough reads.
Thank you.
That's a good question. Yeah. Okay. So what is this not so greedy algorithm? Okay. So as I mentioned, we take insights from this like information limits, right? This information feasibility region. Okay. So basically, I mean, I'm not going to have time to describe in a lot of detail, but just to give you an idea of what that means to take insight from information limits. Okay, so as I just mentioned to you, the true path may need to visit a node more than once. Okay, like in this case here. But then we ask the following question. Okay, so can the true path visit a node more than twice? Okay, so I mean, your answer should be, of course, right? I mean, you can just generalize this situation, right? For example, now I have this path here that visits this node here 3 times, right? It comes like this, then it goes around, then it goes visit twice, 3 times, right? And this comes when you have a triple repeat, right? So a triple repeat like this, right? I get a read in this guy, so a read inside the repeat, then that read should be visited 3 times. Okay, so what's the difference between this case and the previous case? Well, there's actually a difference. So in this case, whenever a node is visited 3 times or more, what happens is I create these 2 cycles here, this blue cycle and this red cycle. And what happens is I can actually interchange the 2, right? So I don't know if my path first goes through the blue cycle and then the red, or if it goes first to the red cycle and then the blue. So this is another sequence which explains the data just as well as the true sequence. In other words, the 2 paths are indistinguishable for any algorithm, right? So there's not enough data for me to achieve perfect assembly with any arbitrary success probability, right? So this means that any situation like this actually lies outside of this feasibility region. And the consequence is then that for points inside the feasibility region, the path visits each node at most 2 times. Okay, so that's just sort of a high-level way to motivate how these information limits can guide the design of the algorithm, because now we know that we should be focusing on paths. If we're interested in the instances inside this region, we should be focusing on graphs that allow the true path to visit each node at most twice. Okay, so we use that in the design of this not so greedy algorithm. So when we design this, when we sparsify this read overlap graph, what we do is we do an edge selection that we call not so greedy. So what we do is we sparsify the graph so that every node has in and out degree at most 2. Right, so the greedy algorithm is extreme in the sense that you only place 1 edge out of each node, and here we're going to basically allow 2. Okay, so as it turns out, 2 is going to be sufficient for us to achieve the feasibility region. Okay, so we're going to end up with a graph that maybe looks something like this. So every node has in degree and out degree at most 2. But now this is still not good. I mean, you still have a lot of like unnecessary edges on this graph. But now this graph has a very nice structure. Okay, so it turns out that a graph with in and out degree at most 2 allows us to prune the remaining spurious edges in a systematic way. And the reason, okay, I'm not going to have time to go into much detail, but that in a graph with this property, with in and out degree at most 2, the edge set uniquely partitions into what we call zigzag components. Okay, so what is these zigzag components? Okay, so for example, I pick this edge here, this yellow edge. Now this node here should have out degree at most 2, so there's at most 1 other edge coming out of it. Now this guy should have in degree at most 2, so there's at most 1 other edge coming in, and I keep repeating this, so I get a zigzag component until it stops. And then I start again some other place. So this way, this partitions the set of edges into these zigzag components. And now each zigzag component essentially induces like a bipartite graph, and we can analyze these bipartite graphs individually and prune them individually. Okay, so I know this is kind of like a lot, but basically we have some rules to prune these bipartite graphs. Okay, so here I'm just showing you some high-level picture of what they look like. So we identify things like this, and we delete some certain edges on these bipartite graphs. Okay, so now this seems like a lot of like ideas, a lot of, and these feel like heuristics, right? But the main point here is that these are not heuristics. Okay, so these are, okay, I'm just showing that, yeah, here we prune these edges. The point is that these are not heuristics. We prove that these deletion rules actually have a theoretical guarantee. Okay, so what we prove is that if we have an instance of the problem that is inside this feasibility region, then the graph that we produced at the end has no spurious edges and no missing edges. Okay, so if you compare with that previous case, that previous technique that I mentioned to you before, where you simply used like a minimum overlap theta, you could never achieve both no spurious edges and no missing edges. But here, we sort of like get the best of both worlds, the best of a small theta and the best of a large theta simultaneously.
So Ilan,
yeah.
So what do you mean by spurious? First, what is the complexity of?
What is the complexity of this algorithm? So there's so the complexity that we prove is for the case of error-free reads. So in the case of error-free reads, we prove a linear time complexity.
Oh, okay, that's cool.
So the problem is, in practice, you need to identify the overlaps first, and that cannot be done in linear time. But yeah. So
you'll need the quadratic time for this, or even more.
Yes. Theoretically, you do need quadratic time to identify the overlaps in practice. Now, the point is that there's software out there that does that, and even with quadratic time, it's fast.
Okay.
So, and it does heavy parallelization and can be done fast. This initial stage of identifying the overlaps.
So I want to try to understand the statement first. So can you explain the theorem in, like, let's say maybe some graph theoretic statement. So you have a directed graph with weighted edges, right?
Yes.
And what do you want to get out of this? So this is the input. What do you want the output to be?
Right. So there's a graph, right? There's this directed read overlap graph, and there is some underlying path on this graph that I want to.
So you're looking for a path.
Yes, it's a generalized Hamiltonian path, right? So it's a path that visits every node and may visit some nodes multiple times.
Okay, and you want the path with the highest weight, or
No. This is just a true path. It's not an optimization-based formulation, right? So I don't want to find a path with a given property. I want to find the true path. So that's kind of another place where this work differs from other approaches, which is that we're talking about finding the true path.
And the weights, so the weights don't matter?
What?
So the weights that you have on the edges, they don't matter for you for when you find the Hamiltonian path?
They do. So yeah, so I mean I kind of like left that out, but in these rules here, these pruning rules, you actually only do the deletion. I mean, you take the weights into consideration to do these deletions.
Before we get to the solution, so the problem is to find a path in the directed graph that satisfies what? Just to make sure I understand the problem.
Right. Yeah. The problem is this, that you cannot really state it in a purely graph theoretic way, because this path is not. It doesn't have. It's just some simple graph-theoretic property. I mean, it's not that the shortest is not the path with the largest weight. There is a true path that underlying the problem. The way, so basically what we show is that if you are in an instance of the problem and that is inside this feasibility region, and this is connected with the actual true sequence, you know, this region is connected with the specific repeat statistics of the genome. So this in a way is what is specifying what the right path is, but in a very non-concrete way.
So is there a unique true path?
Yes, but by definition there's a unique path, right? It's actually no. In general,
the degree is less than 2, less or equal than 2 probably.
So there's a unique sequence. There's a unique true sequence, right? That I'm trying to reconstruct.
Mm-hmm.
You can come up with graphs where there are multiple paths that yield the same sequence. You can do that.
I see.
But yeah, here we prove that if the sequence satisfies some properties and the number of reads and the read length are both large enough, then this algorithm will reconstruct the true sequence, the correct sequence.
And when you said that it's impossible to have the degree more than 2, so is it like, what's the? I didn't get the proof of that.
So I didn't mean that it's impossible to have degree more than 2. The point is that if we have degree, if the true sequence corresponded to a path that had degree more than 2, then this would correspond to an instance of the assembly problem that is essentially outside of the feasibility region, right? Because there are 2 ways by which I can traverse these edges. So there's go ahead.
But isn't there a possibility where the actual where the true path doesn't have this problem? Like, that's what I'm asking.
I see. Yes, so that's true. So you could, in some situations, have even if there are a long triple repeat like this, have a path that does not visit a node 3 times. That is true, but you will still have the same ambiguity. It won't correspond to this, to just swapping the 2 petals, but you will still have multiple paths that are undistinguishable from the point of view of the assembler.
So supposedly that's not solvable. There is no way to solve it.
Yes. So yeah. Okay. So the point is that if you have a triple repeat like this, right, and your reads are shorter than the triple repeat, it's impossible to tell the right order if red comes before or blue comes before.
Okay. Thanks.
Sure. Okay.
And how do you go from the full graph to the graph with degree 2? Is there a systematic way to?
Yes. So that's why we call it a not so greedy, because it's essentially a greedy construction. So you can imagine the following: it's like you have your full graph, right? And now I pick, like, let's say the largest edge on this graph, and I decide to keep it. And then I pick the second largest edge on the graph, and I keep it. And I keep doing that, but under the constraint that the in degree and the out degree at every node is at most 2. Right? So it's kind of like I keep greedily picking the edges, but making sure that no degree exceeds 2.
Oh, okay.
Okay. And so it's kind of like we overshoot a little bit, right? So we put a lot of additional edges, but we're guaranteed that we have enough. And now that then we can come back and do a little bit of deletion at the end.
So somehow there's like one local property and one global property, because if you could do the deletion when you're picking them, why do you have to wait till the end? So
Right. Yeah. So there is exactly. So there is a local property that we exploit, and that, which is what allows us to. So I mean, so this notion that to be inside the feasibility region, your read length should be longer than triple repeats guarantees a local property, which is that the degree 2 is enough. That's the local property, and then but local is not enough to finish the problem. So we need to construct this graph and then look at some more global things like here, right? So
it's not global, right? It's just a neighborhood, small
yeah,
neighborhood.
You're right. Yeah, you're right. It's not global. Yes, yeah, it's true.
So you could do it on the fly. Maybe we just you look at them. Oh, maybe.
Yeah, to some extent, yes. So I mean, I also presented like this for more for sake of presentation, but yeah, you could do things.
So you could do it in an online fashion if that's interesting in practice, but I don't know.
Yes. Actually, that's a very good point. That is something we have considered, which is, you have a data set, you construct this graph, and now I give you a few more reads.
Yeah.
Right? So you want to update this graph, and now you want to So yeah, and the fact that these rules are all local allows you to do that. Yeah, that's a good point. Yeah, so you don't need I think there is a way of doing this in sort of like a one pass. But it doesn't make a huge difference because it's like both of them are linear time. So talking about maybe doubling the time, but it's pretty fast. And it's not really the bottleneck. The bottleneck ends up being that first computation of the overlaps, which is quadratic.
Okay. And if you want to relate it to the pure greedy, this guarantees optimality all the time, right? Whereas pure greedy does not guarantee that you find the sequence.
So the pure greedy does guarantee that if your read length is longer than the.
Oh, okay, yeah.
No, actually, yeah. Even then, you need. If it's significantly longer than all the repeats, then with high probability, yeah, it will have a guarantee also. But it needs a much longer read length.
Okay.
All right. So then we construct this graph, right? And we have this guarantee, right, of no spurious edges and no missing edges. Okay? And just to complete the picture that I mentioned in the beginning, which is, I wanted to get a graph where the true path is an Eulerian path. We're not quite there yet. There's a final step, which is to identify some paths on this graph and actually sort of contract them into a single node like this. Okay, I'm not going to talk much about this, but the point is that after we do these contractions, and it's fairly simple. It's a fairly simple procedure. But once we do that, we end up with a graph, which is an Eulerian graph, and the true sequence now corresponds to an Eulerian path on this graph. And finding an Eulerian path can be done actually in linear time.
Oh.
Okay, so just a recap, right? So we started with this problem where we had this read overlap graph, and our goal was to identify a Hamiltonian path, right? And the problem was, this is an NP-hard problem. So what we showed was that a technique to sparsify this graph down to a graph where the true sequence, right, corresponds to an Eulerian path, which can actually be done in linear time. Right, so this is interesting, right? So those of you who are not paying attention, you just missed the proof that P equals NP, right? Basically, right? So why is this not proving that P equals NP? Right. The reason, right, is this little caveat, which is that we can only do this reduction for for information feasible instances. Right. So okay. So then, as I mentioned at the beginning, so this was all done for error-free reads. Now, and our goal, of course, is to, at the end of the day, deliver something that works for real data, right? And the issue is that long-read sequencing data is very noisy, right? So the error rates are of 15%, and identifying these overlaps is hard. Okay, but fortunately, there are tools out there, and then one such tool is called D-Aligner, and it's actually by that guy Eugene Myers that did the Twitter theorem, right? And basically, what it allows is, so even though this thing has a quadratic complexity, it runs really fast in practice. So we can take the output of the aligner, and that essentially creates the graph, and we can use this not so greedy algorithm to sparsify the graph. Okay, so we did one experiment here with a real data set for E. coli K12. Okay, so this is from PacBio reads. So these reads are 10 kilobases. Okay, so they're much. So the data set is well inside this feasibility region. So if our theory is correct, right, you should be able to achieve perfect assembly. Okay, so when we did this is the sparse read overlap graph that we got. Okay, so it doesn't look very Eulerian. You see a lot of little dead ends sticking out and all kinds of artifacts. So it turns out that, of course, in practice, there's all kinds of issues, and even with the output of the aligner, a lot of things are not perfect. And there's a lot of work that needs to be done to modify Not So Greedy and to just take inspiration in its ideas to come up with an assembler that actually works on real data. So this is the work that we've been doing for months now, and I'm just going to summarize all of that as Not So Greedy 2.0. And with all that, running this Not So Greedy 2.0 on this data set, we actually get this much prettier assembler. So you see that you get these nice these two rings, right? The red and blue ring, and the reason is because real sequencing data, right, is we don't know. So the DNA is a double-stranded molecule. So when I get the reads, I don't know from which strand it came from. So actually, when you construct the graph, you end up with these two cycles as opposed to a single one. Okay, so that's sort of like a proof of concept of the ideas. So this is actually the first part of the talk. I think I'm running a bit over time, so maybe I'll quickly talk about, just quickly mention what the second part would be. So as I mentioned, so this first part was saying that if we focus on the feasible instances, this can lead to new insights in algorithm design, and you can actually design an efficient algorithm that works for all the information feasible instances. Okay, but now, of course, the natural question, and you don't need to be as smart as Alan Turing to ask it, is, okay, but what happens to the other instances of the problem, right? If I have something outside, and that's where we try to introduce a rate distortion perspective to the problem. Okay, so how much time should I?
Maybe 10 minutes.
10 minutes.
For 1 hour, 10 minutes. Do you think 10 minutes you can give us the
high
level idea?
Yeah, I can give you a high-level idea. So the main question here is the following. So we want to talk about partial assembly, right? So your goal is to now say, okay, so I don't have enough data to reconstruct to achieve perfect assembly, but I want to do what's the best thing I can do, right? So in practice, people do that all the time because most data sets in reality you don't have enough data to achieve perfect assembly. So what people usually do is they look at this graph and they measure the quality of the partial assembly in something called N50. So N50 is basically, I'm not going to describe it in too much detail, but the idea is that you identify paths, unambiguous paths on this graph, and each of these paths, they correspond to some subsequence, right? And then, and the N50, you can think of N50 as the median of these lengths. I mean, don't think about it too much. The point is that this is what how people in practice they measure the quality of a graph. Because if, let's say, if I can't achieve perfect assembly, then my assembly is just this graph, right? And the question is, how good of a description of the true sequence this graph is. Okay, so now the problem is this N50 is not very good for several reasons. One of them is that it doesn't really depend on the ground truth, right? N50 is just a metric of the lengths of the paths on this graph, and it doesn't really encode. It doesn't encode in. Okay, I think I may. Trying to think if I start giving too much detail here, I'm gonna. Okay, so let me try to just give a more general overview of this. Right. So the point is that we want to characterize some notion of distortion of a graph. Right. We want to say that you can't achieve perfect assembly. Right. You can't extract a single sequence of the graph, but instead I want to talk about, well, maybe this graph has some distortion with respect to the true sequence. Okay, so just to give you an example here of how we try to quantify this distortion. Okay, so suppose I have this sequence here. It's a circular sequence, right? Because many genomes are circular. Okay, so these two graphs can be seen as assemblies, potential assemblies of the sequence. But which one is better? Which one do you think is a better assembly? Should have a lower distortion, right? So this one on the right should have a lower distortion, right? Because this guy here on the left is essentially a graph that explains every possible sequence. So what we did was we tried to come up with a notion, a measure of distortion here. Okay, so here, for example, if this was your graph, this should have distortion 0 because it's the perfect sequence. And this one should have something like infinity. And now to quantify the distortion of this guy, what we did was we try to essentially count the number of possible sequences that this guy encodes. In this particular case, this guy encodes two sequences, the true one and this other one. So it's kind of like 1 bit of distortion, because there's like 1 bit of uncertainty between these two sequences. Right? So the distortion here should be log of 2, or 1 bit.
Can we ask?
Yeah.
Oh yeah. So can you explain a little bit how does it encode these two graphs?
Yeah. I mean, I can't. It's just that I'm afraid. But yeah, sure. So the point is that
it's okay if we need a little bit more time.
Okay. So of course, a graph like this, it actually encodes an infinite number of sequences, right? I mean, it could go around as many times as I want. But in terms of sequences that have the same sort of complexity as this one, or the same length as this one, is basically just these two, right? Because I mean, you have this option, right? You start like this and you go like this, which is the true sequence. And the only other option that you have is that if you come here and then in the beginning, at this point, you take the other path first, right? Because
so you have to visit every edge once in that small graph at the bottom.
Yes.
Okay.
Yes. So this is just a simple example to sort of like motivate how we're thinking about this notion of distortion. Right? To be a little more precise, we need some definitions, but basically what we do is basically, I mean, we take the true sequence, right? We kind of project it on top of this assembly graph, creating an Eulerian graph. And now we count the number of Eulerian cycles on this graph, right? And we define the distortion as the log of the number of Eulerian cycles. I mean, this is probably not very easy to follow, but the point is that we're kind of trying to come up with a notion that a way to say how ambiguous this graph is, right? And the point is that now, if we look at this, what I've been talking about the whole talk is this: we had this feasibility region, right? You can think of this feasibility region as a set of points for which I can achieve distortion 0. Right. So similarly, you could generalize this and say, well, maybe there should be a region of the set of points where I can achieve distortion 1, right, and then the set of points where I can achieve distortion log of 3, and so on, right? And so you can imagine that this is essentially sort of like a surface here, right, coming out of the screen here. So it's like a so the rate here is sort of like n and l, right? These two parameters are sort of your rate parameter, and you have this distortion surface. And so what we tried to do was to come up with bounds for on this distortion surface, and to analyze this, what we did was we actually focused on cross sections on the surface, right? So we fix some n here, and you can imagine taking a cross section of this surface at that given n, right? So in particular, in the case where n equals infinity, this can actually be computed easily. Okay, so here I'm showing this cross section of this distortion surface when n goes to infinity, right? So basically, I have infinitely many reads, so one can compute this, and this actually serves as a lower bound for all the other cross sections. It's not very hard to convince yourself that when you have infinitely many reads, you should achieve a better distortion than with finitely many reads, right? And then we have again, I'm just gonna summarize all the efforts as not so greedy 3.0, which is essentially an algorithm that now has distortion guarantees as opposed to perfect reconstruction guarantees. It has distortion guarantees. So basically, we have a theorem that, I mean, of course, I'm not gonna read through this. I wasn't gonna read it in the first place, but since we have out of time, basically we have some guarantees on the achieved distortion by this algorithm, and this can actually be computed. Okay, so we get for finite n, right? So here you see in this plot here, I have the lower bound in blue, which is obtained by computing the case where n goes to infinity, and then for finite n's we get these other curves here. And you notice, yeah, so these curves have some gaps, and the reason is because our distortion metric is not defined in every case, and this is really ongoing work. But as you can see, we get upper bounds that are fairly close to the lower bounds. So we're in a way achieving pretty good distortion. Yeah, sorry, I'm kind of rushing through this. I just wanted to give you an idea that so we have this algorithm, and we can actually do this, use this algorithm in practice too. So an experiment that we did was we took that same data set that I showed to you before, where perfect assembly was possible, and then what we did was we truncated the reads. So we shortened all the reads. So basically, we moved this data set outside of the feasibility region, and then we ran this new algorithm, right, which is sort of like tied to, that tries to achieve good distortion. Okay, and this is the assembly that we get. It may not look like it, but it's a good assembly. We get a strongly connected graph and fewer contigs than a state-of-the-art assembler mini-ASM here that I'm showing on the right. Okay, sorry for rushing through all this, but I just wanna give you like the final slide, which is, here we're proposing this idea of focusing on information limits when trying to design these algorithms, right? So first, we showed that by focusing on the instances inside the feasibility region, we can actually build efficient algorithms to solve these instances. And then when you're outside, you can also design efficient algorithms, but they don't try to do perfect assembly. Instead, they try to achieve close, in some sense, to the minimum possible distortion. Okay, so I hope I convinced you that this information limits approach can reveal new insights to the problem. Hopefully, I convinced Alan Turing as well. And yeah, so that's it. Thank you very much for your attention and for your nice questions.
Yeah, thanks, Ilan. So I don't know if anyone has questions. I think we asked enough questions. Yeah, yeah. Go ahead, because we don't see you. Oh, you're back. Oh.
Should I go back to?
In the information feasible region, what happens if you apply the Hamiltonian approach?
I see. So do you mean like applying like algorithms,
Right.
like practical algorithms that try to find Hamiltonian paths?
Yeah, or whatever. Maybe the algorithm that you said, the Pevsner algorithm, for example.
So the Pevsner algorithm, right? What it does is it tries to construct a different graph, which is the De Bruijn graph. So it doesn't really work on these like reads with with high error rates.
Mm-hmm.
Now a good question, which we have thought about. I mean, your question. I mean, about whether we can use like solvers, because there are solvers out there that try to solve the Hamiltonian path problem, right? I mean, it's NP-hard, but people solve these things in practice, right? People solve the traveling salesman problem all the time.
Mm-hmm.
And I think this is a very good question, and we don't really know. I think it has potential. It probably works fine in practice. I don't know. I don't know of anyone that has done that.
Mm-hmm. And just another question. Why do you focus on just one graph from all the reads? Since reading is supposedly getting easier, why can't you construct multiple graphs and then take the
So like the best?
the best or something.
But what do you mean by constructing multiple graphs? You mean like with
I
the
mean,
same
maybe
data
you divide
set?
divide the reads into two parts and then see.
Yeah, actually yes. So I mean in general, like right? I mean you expect your predictive power to be higher the more reads you have.
Right.
So, but it seems that especially in the case of partial assembly, and this is actually something we have been discussing recently, that there may be some gains in doing precisely what you're doing, which is what you're suggesting, which is to divide the data set into smaller sets and running the algorithm in the different in the smaller data sets. It's unclear. It's kind of, this is all sort of new to us, so I don't have a very good answer. But I think there seems to be situations where this is good. Yeah, it's useful.
Thanks.
Sure.
All right. Thank you, Ilan.
Thank you very much.
Bye.
Bye.